TRIUMF. I'm kicking off the physicist presentations, and hopefully in some ways my talk will be a bit of a lead in to some of the other talks. So I'm David. I work in theoretical particle physics, so that means I do calculations, try to make up theories to describe how the universe works. And before I get started, I want to say that it's sort of a tradition in physics, at least, and I think a lot of other sciences, that if you're confused about something or you want to ask a question or you have something to say during the presentation, go ahead, let her know. If I confuse you or if I say something weird or you want to know more, please interrupt me. I invite you to please interrupt me. So I'm going to start off with particle physics because this is what I work on, this is what I know. And I'm going to focus largely on the deconstructive aspect of particle physics. So in some ways, this is the opposite of what many scientists think of as emergence. Well, I'll start by deconstructing and then try to build back up and get to emergence. So we're doing science. This is a cartoon of how science works, at least in physics. So I should say that science is a way of trying to understand how our universe works. It has a set of rules built in. And a big part of these built-in rules is that people are really good at convincing themselves what they want to believe and not what is really out there. So a cornerstone of doing science is doing experiments. So you go, you measure something, and once you measure something, you try to understand what you've measured. So you do your experiment, you do a measurement, and once you have a measurement, you try to describe it. You try to come up with a theory that explains what you saw. So you go off, you work with your theory, you do some work, I work on the theory part, and the others here work on the another part. But you come up with a theory, and if it's a good theory, the theory makes predictions for new experiments, for new measurements. So you go and you do more measurements, and science, in this sense, works in this very collaborative way between theory and experiment. In fact, what Randy and Ingrid said about our collaboration sounds very much like how collaboration works in science. So this is a big picture of science. And as a theorist, I tried to make a checklist of what makes a good theory. So number one, this is always number one, your theory needs to agree with experiments. If you have a theory that doesn't agree with experiments, it's not a good theory, you have to go back. After that, if it's a good theory, it makes predictions. So a theory without predictions isn't very useful either. So I remember opportunities and predictions. And then beyond that, the language we use to write down theories is essentially mathematics. It's not entirely mathematics, but it's mostly mathematics. So you want to be mathematically self-consistent. And included there is logically self-consistent, it makes sense, with reusable theory. And after that, things start to get a little bit more aesthetic. So one thing that drives a lot of us, this is universal, but it's very common, is you want your theory to be as simple as possible, but no simpler. So suppose I have a theory that describes an experiment. If I went off and added some extra decoration to it, in some sense that would make the theory worse. It's something I don't need to describe it. And then beyond that, people start to argue about what makes a good theory. And there's a definite aspect of aesthetics that comes in. So I wanted to go over this because I do theoretical physics. This idea of theory and experiment is a bit unique to physics, to science, and especially in physics. But I wanted to give you an orientation before I go. Okay, so we're doing science. We want to understand our universe. Where do we start? I mean, our universe is very complicated. It's all kinds of things. There's cats and stars, whatever. So where do you start? So a natural thing to start with is try to figure out what things are made of. What are the little building blocks that make up everything else? And in fact, are there even specific building blocks? And this, I think, is a logical way to start. If you have a complicated watch and you want to understand how the watch works, you might be inclined to take it apart and get a desk full of gears. Anyway, so this is essentially what we try to do with the universe. We try to take it apart as much as possible to see if it has any underlying fundamental structure to it. And what we found is that it does. So let's start with something big, an everyday thing, a cat. Cats are ultimately made of a lot of molecules. So you go and you find the cats, and basically everything else that makes up regular stuff is made of molecules. And you can keep on going. Is a molecule the smallest thing there is? The answer is no. It turns out we can subdivide a molecule A molecule is made of smaller pieces called atoms. And then you go and look at an atom, you start to poke it and study it. And then you realize the atom is something I can even subdivide further. You look at the atom very closely, it has sub-pieces. It has things called electrons, and then it has a core that we call the nucleus of the atom. So as far as you know, electrons are fundamental particles. You can't split them up any further. They're a fundamental building block of the universe. So this is good. We've at least gotten part of the way finding fundamental pieces. Then we go look at the nucleus, and it turns out the nucleus isn't fundamental. The nucleus itself is made of even smaller things than a nucleus. The nucleus is made up of pieces called protons and neutrons. And in fact, the protons and neutrons aren't even fundamental. The protons and neutrons themselves are made up of conglomerations of things that we call quarks. So specifically what quarks are, what protons and neutrons are, isn't so important, but I want to say that we can get down to a level where we have quarks and we have electrons, and we can try to write down a theory for those basic building blocks that seem to be fundamental. As far as we know, they're not made of anything smaller. And we can try to start with a theory of these fundamental constituents and then build everything back up. So over hundreds of years, especially the past 100 years, this sort of deconstructive approach has been a major focus of scientific progress. And this is the result. So we spent over 100 years, billions of dollars, lots of brain power, lots of time, lots of headaches and coffee and so on. And we think we found the set of elementary building blocks of all the regular stuff around us, all regular matter, and in fact, all matter that we'd be able to see so far in the little organ. So there are things called quarks, there's things called leptons. The lepton includes the electron, so we find electrons in atoms. The quarks clump together. To make these protons and neutrons and make atomic nuclei, and then you start building them up. So we think we have the sort of fundamental pieces. This whole structure, we give it a fancy name called the standard model. We're not so good at naming. But we have a name for our theory of fundamental constituents. It's called the standard model. These are the elements of the standard model. These are the pieces inside it. And within our standard model theory, we also have a description of how these pieces interact with each other. So we have a set of rules of, the standard model basically tells you what the things are in it that are fundamental, and it gives you a set of rules for how they interact. So everything you could possibly want to know about these things is included in the standard model. So great. We made a lot of progress. In fact, the standard model might seem like a little bit overkill, because if you just focus on regular matter, not stuff that you make in very high energy experiments and so on, it turns out that only a subset of the whole standard model actually comes up. I'm just mentioning this, that the standard model seems to have more stuff than you actually quote unquote need, but this is what we got. So great. We have a standard model. We have a pretty good understanding of what we think are the fundamental constituents of the universe, and certainly the fundamental constituents of everything that makes up what we call regular matter, the stuff around us. It's quarks and electrons and stuff all clumped together. So we think we know what the building blocks of a table or me or whatever else are. So this is great. So are we there? Do we have a theory for how the universe works? Are we done science? Can we go home and I don't know what else you do, but are we there yet? And not surprisingly, the answer is no. So suppose I take the point of view that, okay, great, I have my standard model. Let's start there. Can I start with my standard model and build up the full complicated structure of the whole universe, the cats and the stars and the galaxies and all that? And the answer is no. We don't know how to go backwards. And in some sense, when physicists talk about emergence, it's this inability to go from what we think of as fundamental building blocks to describe the rest of our universe that we call emergence. So maybe to give you a better example, to go from quarks to atomic nuclei, this is the whole field of nuclear physics. This is a major topic of fundamental research we do here. So the fact that it's a major topic of fundamental research means that we don't know the answer. So even from this step to here, submicroscopic, subatomic, we don't know what's going on. From atoms, from nuclei to atoms, this is atomic physics. Chemistry is making molecules out of atoms. Biology is making cats out of molecules and so on. I'm not quite doing this stuff dark justice, but you get the idea. the whole field of research, and we don't know how to do this. So even though we know the fundamental pieces, we don't know how to build up the full-size stuff out of it. And there are basically two reasons for this. So one is, it sounds a bit prosaic, but it's actually very deep, and Jess will get to this a little bit in his talk. Big things, like cats or even big molecules, are too complicated for us to compute. Even though we know the pieces that make them up, they're just too big, too complicated for us to do a reasonable calculation in any logical way to get the answer. They're just too complicated. And in this sense, we see emergence of complicated structures out of very simple building pieces. There's also a second aspect, though, and this gets back to what I work on, which is fundamental physics and the elementary constituents. We also don't understand the fundamental constituents themselves well enough to get the full description of the universe. So there are lots and lots of examples of this, but I'm going to concentrate on one. So this might seem a bit perverse. So I told you that it's already hard to describe big things using small things. So I'm going to go even bigger things. I'm going to zoom out. And in fact, zoom out basically as far as you can zoom out using telescope and so on. So if I zoom out, you see, so here's our Earth, here's a star. In this case, it's the sun. The sun is a star, it's a hot ball of burning gas. And the sun is just one star of billions and billions within our galaxy. So here's our galaxy, and each little kind of point of light within the galaxy is a single star. We're in a galaxy, our galaxy is called Milky Way. There's lots of other galaxies out there. Our galaxy and other galaxies are typically parts of bigger conglomerations of galaxies called galaxy clusters. So here's a galaxy cluster, a bunch of different galaxies all connected through their mutual gravity. And you keep on zooming out. And when you keep on zooming out, you see sort of an interesting pattern we call cosmic structure. So the pattern of cosmic structure is sometimes referred to as filaments and voids. You see like the little light point here, this little dot here, this is a whole galaxy cluster. You keep on zooming out, bigger, 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 and you see the structure of filaments, of kind of galaxies and galaxy clusters that are connecting with each other, separated by big, huge regions of just empty space, nearly empty space. So in some ways, zooming out is a bit simpler than trying to study things like cats. Zooming out, there's a sense in which things are just interacting with their gravity. I know how gravity works, it shouldn't be too bad. But even this, it turns out that we don't know how to do. And one thing that comes up when you try to study understand the structure of things like filaments and voids, cosmic structure, or even galaxies themselves or galaxy clusters, and this comes up in a lot of different observations, if you try to describe this stuff with the stuff we know, with the particles in the standard model and build it up, it turns out that we're just not able to describe what we see in observations. Known matter doesn't describe these filaments and voids. It doesn't describe how galaxies move around, how galaxy clusters move around, and their kind of shapes and structure and so on. So here, beyond just not being able to build up big things out of little things, there's an even worse problem. And an even worse problem is that we're missing something. To explain the structure of this stuff, it turns out that you need a lot more matter than what you can account for with the matter that we know of, the stuff in the standard model. So there has to be some new fundamental, we think there has to be some new fundamental matter, we call it dark matter, that is present in things like galaxies and galaxy clusters and superclusters and so on, to give rise to this set of observations you get from this drawing. So roughly we think about a quarter of all the matter in the universe is just regular matter, the stuff we're familiar with, the stuff we know of. The other 3/4 is this stuff we call dark matter. And one of the things that I work on, and what other people in the lab are working on, is trying to figure out what it is. Hopefully this animation will play. So this is an example. This is one of sort of infinite numbers of examples of emergence in physics. This is an example of starting off in a very, very early universe, a long, long time ago. And a long, long time ago, it turns out that our universe was very, very uniform. It's not as kind of stringy and filament and voidy as it is today. And people do simulations of what happens as you go forward in time, assuming you have dark matter. And this is what happens. So this is a simulation of cosmic structure forming. So you start from a very, very uniform early universe. And thanks to dark matter and gravity, The small deviations from this very uniform start. The small deviations from the very uniform start become very non-uniform. This structure of filaments and voids emerges from a very uniform start, thanks to gravity and dark matter. And it turns out that you can actually put numbers on the pattern of filaments and voids you get. And to match what you observe, you need a lot more matter than what you can explain with just regular matter, the matter you can essentially see. And this is where dark matter comes in. The picture is that dark matter comes in, it collapses, and it pulls in regular matter, and the regular matter then does its thing and makes up stars and galaxies and us. So dark matter, if you like, is sort of a scaffolding upon which the rest of us and our galaxies and universe and so on are built. But the thing is, we don't know what dark matter is. We have no idea. We know it's not regular matter, but that's about it. You had a question?
Yeah, was the entropy increasing there?
Yes, yeah. So it always goes up, but yes, in this case it does too.
Because it seems kind of counterintuitive. It seems like it's decreasing.
So
you started with something so uniform, and it gained structure.
Yeah, so in some ways the uniform is actually a lower entropy than non-uniform. So the uniform in some ways has a lot of symmetry. If it's uniform, it looks the same in any direction. Whereas after it collapses, it looks very different from one place to another. And the way entropy counting works, it turns out that gives you higher entropy. It's a bit counterintuitive, but it turns out to be. So here is a kind of zoomed in picture. Scientists do these enormous simulations of dark matter collapsing and forming structure. And this is roughly almost the size of the observable universe in their simulation. And then they zoom in, zoom in, zoom in, and you get all the way up to a galaxy cluster. And for this all to work, for it all to make sense, you need dark matter, you need more stuff. So I'm going to wrap it up there. My apologies again for the computer crash. So from a strict science point of view, often what we mean by emergence is that we don't know how to build up the big universe out of the simple building blocks. We think we understand pretty well, but not entirely. So I've got a bit over time. I don't want to go too further, but again, thank you, and I'm happy to answer questions.
I have a quick question. So, dark matter is the explanation to explain phenomena of kind of the changing universe in some way. And so dark matter is another way of describing gravity.
Well, it's something that, yeah, so dark matter is our best guess. The other approach is that gravity doesn't work the way we think it does. It turns out that the dark matter explanation seems to work a whole lot better. And a lot of that comes from the fact that we have observations that seem to require dark matter over very, very different sizes. So there's evidence for dark matter from individual galaxies, but also from the much, much larger galaxy clusters, all the way up to the entire size of the observable universe. And this is a huge different range. And typically, when we start tinkering with gravity, gravity works kind of normally, the way we think it does, which we measure very well kind of around our solar system, but it has to change at some point into this kind of different thing. And usually when gravity changes, it changes at all lengths of all lengths kind of above this change point. And but the thing is, we have evidence for dark matter on these very, very different length scales. So I don't know of a good way to modify gravity to do all the things that just a simple dark matter hypothesis would just more matter than we do.
So dark matter is a way for you to acknowledge that you don't know, but it puts that not knowing within a term, within a concept, and allows for future emergent theories to flesh out what dark matter is.
It's a bit more than that. It's a bit more than that in that it's sort of a simple theory, if you like, that there's more matter than we know of. It just happens to not give up much light, so it's very hard to see. That's what we call it dark. But this is a very simple explanation. This gets back to the simplicity question. That this very simple assumption that there's more matter, that we don't know what it is, explains this whole range of data, means it's a good theory. Whereas tinkering with gravity can typically explain one bit of data, but not something else. And if you try to tinker with gravity so it changes and then changes and changes to explain all the observations, that gets into a huge complicated mess. And from the point of view of simplicity, dark matter is a much nicer theory. So this is actually getting to this aesthetic part of ranking theories, if you like. The dark matter is an attractive theory simply because it is so simple and explains such a range of different phenomena.
I've heard sometimes people say that you get the idea better if you just, what I call it, transparent matter. Like it's matter that we know is out there because of its gravitational effect, but you can't see it. You can see through it. You wouldn't know. Can't see it with the telescope. It doesn't light up. It does have other effects, but it's just dark because it doesn't light up.
Sure, yes.
Yeah, you know what I mean. You just say transparent matter. People may say, "Oh, I see what you mean. It's out there, but you can't see it."
I have a question that is maybe it's not related to dark matter, but I'm curious why you have the Higgs boson holding the other particles instead of with the others.
Yeah, so okay, there's a little bit of it. There's also a little bit of it there. Okay, so the two reasons for it. Yeah, it's a good question. So first of all, it turns out that all the masses of everything within the Standard Model, the fundamental masses, all derive from the Higgs boson. So from this point of view, that the Higgs is kind of a structure that supports the rest of the theory. So that's where the finger holding things up. The inside joke is that it's a picture of Atlas, and one of the experiments that found the Higgs boson was the Atlas experiment. And we have people here working on Atlas. So that's part number 2. Yes.
So I don't know if this makes sense, but how does time come into play with dark matter? Or does it? Or does it not?
So it comes in. Maybe I don't want to say in an uninteresting way. It comes in the sense that there's a whole story of how dark matter came to be. So the whole story of time evolution, if you like, where you start off in a very, very hot early universe, it's very uniform, and then the universe expands and cools off. So Big Bang picture, you start with a very hot state, it expands and cools off. And as it expands and cools off, dark matter, in some sense, forms, or at least dark matter comes about with a amount of dark matter that's much bigger than kind of other kinds of matter. So there is a storytelling in the sense of a cosmological history of how dark matter came to be, and then what dark matter did later on in terms of collapsing through gravity to make the structure on which regular galaxies and stars and so on form. So there's a whole story of the history of the universe where dark matter plays an important role. So time comes in that sense. On the other hand, it's fairly standard time evolution from the point of view of the equations we write down. Whereas time comes in much more curious ways in certain theories to describe how gravity works in conjunction with quantum mechanics. So time is essential and it is a story, but time really gets weird when you start doing what's called quantum gravity.
If all matter interacts with gravity and the universe is expanding, I mean, shouldn't it collapse? Should it stay put? Like, why is it expanding?
Okay, I guess saying general relativity is not a good answer. That's a good answer. No.
I think they constantly check.
No, there's a good answer. I'm just trying to remember.
Can't you label it ongoing research? I mean...
No, there's a standard explanation that I don't remember. I'm sorry, I don't have something better than that. I'll come up with it and get back to you. Okay. But my apologies.
And then lastly, with dark matter, is it called dark matter because light doesn't interact with it, or because we just don't know what it is and we're in the dark?
Yeah, so because we haven't seen it, and we try to see it, we point to telescopes all over the place looking for it, there's a limit on how much light it can give out. And that amount of light is very small.
And it's very far away from us. Like, we're in a cluster right now, so dark matter's not like right here.
Oh, no, it is right here.
It is right here.
Yeah. So in the picture, I was looking for dark matter right here in the lab. So we actually think it's all over the place.
Okay.
It's zipping through us, it's going through our bodies. And we can't see it just because it's, like Des said, very close to transparent. It doesn't talk to regular matter very much. So for most of the time, it's all around us, but it's just zipping right through us. I don't know how to,
I've been waiting a while.
okay.
Maybe one more, Ben, one
Okay.
last question, and then we'll go, and then we'll have more time for questions.
So I've been thinking about this clustering thing for a while, and it seems to me if the normal matter was somewhat evenly distributed, those pieces would be the same distance apart from each other, so they wouldn't cluster up because some wouldn't be closer to others than other ones are, meaning they're evenly distributed. So when we're talking about dark matter solving that problem, is it because dark matter is also uniformly distributed in the early universe? And somehow just there being more of it means the likelihood of some being closer to others is greater? Or is it because the distribution of dark matter in the universe was already unevenly distributed and the filaments follow that structure?
Yeah, so if you look back as far as you can, using visible light, or effectively visible light, light goes along at some finite speed. It doesn't go infinitely fast. So if you look far away, that means that you're seeing light that was emitted a long, long time ago. So if you look back as far as you can, you're effectively looking back in time. And as you look further and further back in time, you see that the universe was more and more uniform. So it was never exactly uniform, but it was very, very close to uniform. So like so deviations from uniformity were like 1 part in 10,000. And it turns out that this 1 part in 10,000 deviation from uniformity is enough to lead to this structure we see today, but only if you have enough matter. So we think that the dark matter fluctuations and the regular matter fluctuations were about the same early on. It's just you need a whole lot more matter than we could account for with regular stuff for it to collapse this way.
Great, thanks.